Hello Math 1324 students. Let's begin Lesson 12, Exponential and Logarithmic Equations. Previously in Lesson 11, we studied exponential and logarithmic functions. Let's review those just a little bit, as briefly as possible. This is how we define the exponential function, a to the x power, where a is greater than 1. Did I say greater than 1? Excuse me. The base a is greater than 0. Sorry about that. The base a is greater than 0. Now when a is greater than 1, as you can see here, the graph must be increasing. When a is less than 1 but still greater than 0, graph must be decreasing. Here in this notebook, I use the examples a equal to 3/2, 2, and 3 for case 1, and their reciprocals 2/3, 1/2, and 1/3 respectively as case 2, along with appropriate color coding. Please note the symmetry. And why do we have the symmetry, by the way? Those are related to these. The reciprocal to the x power can be rewritten as original to the negative x power. So yes, we do. We do have this symmetry with respect to the vertical line. Next, we have some common properties like this. Domain is negative infinity to positive infinity. Okay, that's easy to see. Basically, it's repeated multiplication, division, and radical how many times. Yeah, you can denote how many times. No problem there. And then the completion. Now, the range is 0 to infinity, which means all positive. All strictly positive. That too is pretty easy to understand. No matter how many multiplication, division, radical you do to a positive number, you have to stay positive. You can get closer and closer and closer to 0, but never equal to 0. So this is wrong. This is right. It has to be open interval, 0 to infinity, strictly positive. And the y-intercept is 1, as you can see here and there. That's because a to the 0 power is 1. And then we have some further asymptotic behavior here. A to the infinity power, that means if I go to the right, goes up to positive infinity. That's when a is greater than 1, because basically we are multiplying a over and over again. Repeated multiplication of a, which is greater than 1, yeah, that'll make things much bigger to infinity. And how about the other direction? Repeated division of a, which is greater than 1, that'll make things smaller, but still positive, but getting infinitesimally small. So we have this asymptotic behavior to negative infinity going down to 0. Now when a is less than 1, it's the opposite. Precisely the other behavior, because they are related to the reciprocal, so basically it's flipping up. Finally, in a special case, when a is 1, then we get 1 to the x power, which is constantly 1. So we just get a horizontal line y equals to 1, so it's not very interesting, nor important. Alright, so much for the review on exponential functions. Now how about the log functions? The log functions were defined as the inverse function, as you can see in this visualization. Blue is the original exponential function when a is greater than 1, and red is its inverse function, log base a of x. And as you can see, these two graphs are symmetric with respect to y equals to x, the principal diagonal. The reason? Consider this as a graphic paper, and you're folding that graphic paper over this line, the principal diagonal, y equals to x. If you do that, then you'll see that the x-axis is going to be folded right onto the y-axis and vice versa. And that action is precisely the same action that goes on for inverse function. X goes to y, and y comes back to x. You see? So they're the same geometrically. And that's why we have to have this behavior, symmetry with respect to the principal diagonal. Now this program is randomized, so if you run again, you're going to get different a value. still different A values, but no matter how many times you run, you still have to have the symmetry and the inner set, 0, 1 and 1, 0. Now, when A is less than 1, we have decreasing graphs like these with similar properties, but these are far less important, so let's not worry too much about those. And then instead, let's go over to the properties by putting these two together. These are inverse functions, so all properties of inverse functions apply. Domain becomes range, range becomes domain. Yeah, x is going to y, y is coming back to x, you see. And then inverse and original cancel each other out. So x goes to y and y coming back to x, so staying at x, basically. So log of exponential or exponential of log, they cancel each other out and we just get x back as long as we have the same base. Here's an example. A to the 0 power is 1. Yeah, 0 power is defined as 1. Everybody knows that. But that's why log a of 1 is log a of a to the 0 power, because you see a to the 0 power is 1. And then we can apply the cancellation rule. Log of a, exponential a, base a, cancel each other out, then we just get 0. This one here. Okay, so much for review on exponential and logarithmic functions in general. And now let's focus upon the natural exponential and the natural logarithmic functions. Let's consider a special base e, which has a value 2.718 something something. That's an irrational number, so it goes on forever with no repeating pattern. This number is called Euler number and represented as the alphabet e. So if we take e to the x power, that's a natural exponential function, and the inverse of that, log base e of x, or abbreviated ln of x, that's a natural logarithmic function. So e is 2.718 something something, so that's greater than 2 but less than 3, so it's got to be somewhere in between green and red, closer to green, because 2.7 something. In general, we have this kind of graph, but please note that I drew not just curves, but some lines. Let's see, what is this green line? This is y equals to x, the principal diagonal, so that the exponential function, e to the x power, and then the logarithmic function, y equals to natural log of x, are symmetric with respect to the diagonal y equals to x, because they are inverse of each other. We discussed this behavior already. Moreover, let's pay attention to these dotted lines. At the inner set, 0, 1 and 1, 0, the slope is 1. That's why the slope of tangent line here is 1 and also 1, and that green has slope 1, so they're all parallel. Do you see the parallel behavior? This slope behavior at the intersects make the natural exponential and natural logarithmic functions just right, basically. Kind of like Goldilocks function, so to speak. Not too steep, not too flat, just right. And because of that, the computation, especially the computation in calculus, for the natural exponential and natural logarithmic function is much, much easier than those of the other exponential and logarithmic functions. At this level, however, I cannot give you any further motivation. I can still give you these. Look at these examples. They're all natural log problems. Again here, all natural log problems. Let's go to section 2. What do you see? These are all natural exponential problems, and then natural log problems. Yes, of course, we see some harder problems with arbitrary bases, but they are rather exceptional, and basically they are A-level problems, maybe even extra credit. In short, the overwhelming majority of our focus of attention will be the natural exponential and the natural logarithmic functions from this point on. Keep those in your mind. Now, there's one more to review, exponential and logarithmic rules. Okay, exponential rules, let's do this very, very quickly because this one goes way, way back to pre-algebra, elementary algebra, intermediate algebra, those days. A to the 0 power is 1, not 0, but 1. First power is itself a, so if there's nothing there on top, that means 1 is hidden. Negative first power is reciprocal, 1 over a. Negative x power is reciprocal of x power, 1 over a to the x power. All good? Now let's go to the second line. Multiply the exponentials, we add up the power. Divide the exponentials, we subtract the power. Exponential of exponential, or power of power, we multiply the powers, as long as we have the same base. Now what if you have different bases like these? We distribute the power, either like this or like that, and so on and so forth. Okay, so much for exponent rules. Now log rule number 1, cancellation. Log and exponential cancel each other out, like this or like that. And then here are a couple of applications. A to the first power, after cancellation you get 1. And then 1, that's a to the 0 power, so after cancellation we get 0. Okay, so much for cancellation rules, and then we have standard log rules here. Log of x times y is log of x plus log of y. Log of x divided by y is log of x minus log of y. And log of x to the k power, k is multiplied up front. And this one works not just for positive integer k, but for anything. If it is radical, then this can be 1/2 power for square root, 1/3 power for cubing root, and so on. It works for those two. Multiply by 1/2, multiply by 1/3, and so on and so forth. Here's the same rule in natural exponential version, natural exponential, natural logarithmic version. Here's a warning. Log of x plus y is not log of x plus log of y. Log of x plus log of y is actually log of x times y. Same thing goes here. Log of x times log of y is not log of x times y. Log of x times y is in fact log of x plus log of y. So be careful about these kind of things, especially on the left-hand side. Okay, finally one more. Change your basis. So any a to the x power, we can change it into the natural exponential by taking this rule, e to the x log of a. Arbitrary base log base a of x, you can change it into natural log by log of x over natural log of a. So these rules allow, these rules allow us to change arbitrary exponential and logarithmic expressions into the natural exponential and natural logarithm. So 90% of the time, once you get through with this class, I mean in this class, at this level, we're just learning exponential and logs, so we deal with arbitrary bases too. But once you get past 90% of the time, maybe 99% of the time, you're going to deal with natural exponential and natural logarithms only, because they can be all transformed into these, and then everything can be rewritten in terms of natural exponential and natural logarithms. So there goes the review, and then we're going to go with some example problems that will require these, especially the second rule here. Okay, we're going to do those example problems in a separate video, so stay tuned. See you soon.